Hello everyone, and thanks for watching Edupedia World videos. Up till now we've seen how to solve problems involving motion in one dimension, and now we'll expand our knowledge into solving problems in motion in two dimensions as well. Let's take a quick recap of what we've learned so far. Whenever we solve a problem involving motion in one dimension, there are a certain number of things we need to keep in mind. The first is we need to decide between which two events are we applying the equation. Then we need to decide which equation should we use. Now how do we decide which equation should we use? We know that there are a total of 5 unknown quantities: the displacement, the initial velocity, the final velocity, the acceleration and time. And we know that we need any 3 out of the 5 quantities, and we'll be able to find the other 2. Based on which 3 quantities we know, we can decide which equation to use. For example, if I know V, U and T, and I need to find A, I can use the first equation, V is equal to U plus AT. If I needed to find S, I could have used another equation. Also, another thing to note is that the first step is between which two events. So if I take two events, S will be the displacement between the two events, U will be the initial velocity, that is the velocity at the first event, V is the final velocity, that is the velocity at the second event, A is the acceleration, and T is the time interval between the two events. It doesn't matter whether A is the acceleration at the initial event or the final event, because the equations we've learned so far are only valid when the acceleration is constant between the two events. That means the acceleration at the first event is the same as the acceleration at the second event, which is the same as the acceleration at any time between the two events. So now we'll move on to motion in two dimensions. These are the 4 equations which we've seen. The first, third and fourth are your basic equations. The second equation is derived from them, and it just says that the displacement is average velocity multiplied by the time. So let's take a couple of examples. Let's say I'm standing at the edge of a cliff and I drop a ball. These photographs of the ball drawn can be assumed to be drawn at equal intervals of time. Let's say at intervals of 1 second each. So at t is equal to 0 seconds, this is the position of the ball near my hand. This is the position at t is equal to 1 second. T is equal to 2, t is equal to 3, t is equal to 4, t is equal to 5. We see that because of the gravity, the ball falls in a straight line towards the center of the earth, and this is motion in one dimension. Another thing to note is that the consecutive distances between the balls increases as time passes. This signifies that the ball is speeding up or accelerating. The displacement between t is equal to 0 and t is equal to 1 second would be the average velocity multiplied by 1 second, and it's quite small because the average velocity is quite small in this interval. In the next interval, the speed increases, and so the distance between the two balls increases. In the third interval, the distance is even more, and it keeps on increasing as time passes. This is another example of motion in one dimension, and in this case we throw a ball vertically upwards, and we see that after consecutive intervals of time, the successful distances between the balls decreases for a certain time. So this is the position of the ball at t is equal to 1 second, 2, 3, 4, 5, 6, 7, 8 and 9. And it travels a large distance between t is equal to 0 and 1 seconds, and a smaller distance between t is equal to 1 and 2 seconds. Smaller still, smaller, and then it starts increasing. This signifies that initially the ball is speeding down or decelerating, and then it is speeding up or accelerating. Now let's say we do the very same experiment, but we do it in a place which has a constant wind from left to right. So because of the wind, the ball not only moves up and down, but also shifts towards the right a little bit. So if there was no wind, the ball would have been at this place at t is equal to 1 second. But because there is a wind, the ball shifts slightly towards the right. If there was no wind, this would have been the position of the ball at t is equal to 2 seconds. But because there is wind, this is the position of the ball. In fact, if there were no wind, the trajectory of the ball would be exactly the same as it is in this figure. But because there is a wind, every interval of time, the ball moves a certain distance towards the right. And this trajectory is basically this trajectory, where each and every one of the balls is shifted towards the right by a certain amount. And we see that this motion is not in a straight line, and it's called two dimensions, or motion in a plane. Let's look at an example a little bit more clearly. Let's say I throw an object in a horizontal direction from the edge of a cliff. If there were no gravity, then Newton's first law would be valid, and the object would move in a straight line forever and ever until the end of time. And since there would be no acceleration, it would cover equal distances in equal intervals of time. Now let's say instead of throwing the ball, I just drop it in a place which has gravity. The motion would be what we saw right now, It would cover a small distance in the first interval, a larger distance in the second interval, and even larger in the third, and so on. All we need to do to calculate the actual motion of the ball is add these two. And we'll see in a moment mathematically as well that motion in 2 dimensions can simply be resolved as two perpendicular motions in 1 dimension each. So we calculate the x displacement based on motion in the x direction, and we calculate the y displacement based on motion in the y direction. The x displacement basically gives us the x coordinate and the y displacement gives us the y coordinate. We plot the point and this gives us the actual trajectory of motion of the particle. Another thing to see is in that the y direction the distances increase as time passes, but in the x direction these distances are constant, signifying that in the x direction the acceleration is 0, which is true because we know gravity only acts in the vertical direction. So let's look at this in a little bit more detail. The first equation we saw was v equals u+at. But this is actually a vector equation, so I need to put arrows in front of all of these. V is a vector, u is a vector, and at is a vector. At is the product of a vector and a scalar. It is the product of the acceleration and the time, and the product of a scalar and a vector is a vector. What this equation says is that there must be a vector u and another vector at, which would be a multiplied by t, and when we add the two vectors we get a third vector u+at. I'm adding using the triangle rule of addition here, and we know there's another vector v, and what this equation says is that the vector v and the vector u+at are equal. Now if two vectors are equal, that means everything about them is the same. Their magnitudes are the same, their directions are the same, their components along any direction are the same. So when we say these two vectors are equal, we can also say that their components along, say, the x-axis are equal. So we denote components as subscripts. So we can also write the equation Vx is equal to ux plus the x component of at, which would simply be the x component of a multiplied by the t. Similarly, we could write the same equation in the y direction. So it would be Vy equals uy plus ayt. These two equations come from this particular equation, saying that these two vectors are equal, so their components along the x direction should be equal and their components along the y direction should be equal. So we see a very nice result, which is the x component of the velocities and the acceleration follow a simple equation Vx is equal to ux plus ax times t, and the y components follow the equation Vy is equal to uy plus ay times t. So we see that we've mathematically been able to resolve a motion in a plane into a motion in two separate 1 dimensions, and the generalization to 3 dimensions is easy enough. A motion in 3 dimensions can be resolved into 3 perpendicular motions in 1 dimension each. The same goes for the other equations. We know that s is equal to ut plus half at square, so sx equals ux plus half axt square, and sy equals ui plus half ayt square. Right, and the same goes for the third equation as well. Vx square is equal to ux square plus 2ax dot sx, and vy square is equal to ui square plus 2ay dot sy. So we see that we'll be able to apply any equation, and the steps we needed earlier were we decided the events, we decided the equation to use, and we made sure that the acceleration is constant, and we've just added one more step to the equations now. So these are the 4 things we needed to keep in mind earlier. Now I've added a 5th thing to the list. We need to also decide in which direction are we applying the equation. So let's say I've decided that I'm applying the equation between events A and B, and I'm applying the first equation, v is equal to u+at. Then I need to decide in which direction am I applying the equation. So I could take the direction as x-axis, y-axis, or any other complicated direction, and I would take all the components of the vectors in the equation along that particular direction. So I could apply the equation at in the direction northwest, and then v in the direction northwest would be u in the direction northwest plus at in the direction northwest. That would be a in the direction northwest multiplied by t. So this is just one simple addition which we need to do, and now we'll be able to solve problems involving motion in 2 dimensions. So let's look at the standard problem which we solve, which will be the problem of projectile motion. This is my x-axis. This is my y-axis. Keep in mind, the moment I draw the axis, I've also decided the directions which are positive. The right direction is positive in the x, and the upward direction is positive in the y. The general problem which is given to us is, we throw an object with the speed u at an angle theta with the horizontal, and we'll try to solve it on the standard scenario in which there is gravity acting in the vertically downward direction and no acceleration in the no acceleration in the horizontal direction. So the net motion of the particle would be something like this. This is what we would call projectile motion, and we see that it's not along a straight line. In fact, it's in a plane, the xy plane. So the first step would be to resolve everything along the 2 directions. So, sorry, not vx, ux would be the component of u along the x direction. We've seen how to calculate components in the lesson on vectors. U cos theta will be the component of u along the x direction. So it will be u cos theta. Similarly, uy will be u sin theta. What is ax and ay? Ax will be 0 and ay will be minus g. And this is because the acceleration is g in the vertically downward direction. So its x component is 0 and its y component is minus g, because we've taken the vertically upward direction to be positive. So we see that in the x and y direction we've already gotten 2 out of the 5. We are already given u and a. The left things are s, v and t. If we find any one of the 3, we'll be able to find the other 2, because we only need 3 out of the 5. The things we will try to calculate are the time of flight, which is the time taken in the particle from going from this point to this point. I just label these points as, let's call this A, let's call this point B, and let's call this point C. The time of flight will be the time between the events A and C. Then we'll try to calculate the horizontal range. Horizontal range is the distance AC. It is the horizontal distance the particle travels. And then we'll calculate the maximum height, which is the height of B from the ground. That is the maximum height reached by the particle. So we'll always try to go through the algorithm which I've provided, and we'll see that minimizes the errors. So the first step is to calculate the time of flight. So the first step which we need is, we need to decide between which 2 events are we calculating it. So we could use the events A and B, B and C, or A and C. But in this case, since we need the time interval between A and C, it makes sense to apply the equation between the events A and C. So now we've decided the events. Now we need to decide which equation should we use. So for that we need to know what are our knowns. U and A are known, obviously. We need to find out T. So we need either S or V. We don't know V, but we do know S. You might say we don't know S because we don't know the distance AC. That's what we're trying to find out. But keep in mind, since we are applying the equation in the vertical direction, we need the displacement in the vertical direction, and AC is pointing in the horizontal direction. So the component of AC in the vertical direction is 0. So we know that between A and C, SY is 0. Right? You can see that because A and C are both at the same vertical heights, which is 0. They're both on the ground. So between A and C, we know SY. By the way, the equation wouldn't have worked in the x direction because we don't know Vx or Sx. We don't know Vy, but we do know Sy. So we will be able to calculate time in the y direction. So let's do it. We know Uy, we know Ay, we know Sy, and we want to calculate the time. So we'll use the second equation. That is 0, that is Sy, is equal to Uyt, that is u sin theta t, plus half at square, that is minus half gt square, because a is minus g. which gives me time. I write it as capital T because this is the time of flight, a very specific quantity. We find it to be 2u sine theta by g. And this is the formula which you should remember, but I would suggest it's more important to know how these formulas are derived than to actually remember them. So what do you need to do to calculate time? Just simply go through the algorithm, decide the events. We saw that the events A and C, what was it needed? Because we needed time between A and C. Decide the equations. We decided to use the second equation because we knew the S in the Y direction. So in the Y direction we knew U, A and S. If we wanted to find, we could calculate V as well, but here we only need T, so we calculated T. So this is the time of flight of a projectile. This is the total time the projectile spends in the air. Let's try to find the horizontal range. The horizontal range is the displacement in the X direction, and it is the displacement between A and C. So the first step is already done. We know the events between which to apply the equation. The events will be A and C. We know two things. We know UX and we know AX. Do we know anything else? Do we know the final speed? No, we don't know that. Do we know the time? Well, we didn't earlier, but now we do. The time is the time of flight, right? We just calculated it. So we know between A and C, the time is 2u sine theta by g. So we can calculate displacement using the second equation. The second equation gives me S, which is what we need to find out, Sx, which is the range, it is denoted by R, is ut plus half at square. Ut will be ux times t. So u cos theta times t. T will be the time we just found out. 2u sine theta by g. Plus half at square, but that will be a big 0 because ax is 0. So this will give me R is equal to 2u squared sine theta cos theta by g. And if you've done a little bit of trigonometry, you know that sine 2 theta is 2 sine theta cos theta. So this is also often written as u square sine, u square sine 2 theta by g. So this gives me the second important formula, the range, the horizontal distance traveled by the projectile. And we need to find out the third thing, which is the maximum height. The maximum height, by definition, is this distance. It is the height between A and B. So the best thing to, you cannot apply the equation between A and C in this case because that will give me Sy equals 0. In fact, that's what we used earlier in this place. So we'll need to apply the equation between either A and B or B and C. I'll do A and B. You can try A and C, B and C at home and see that it will give the same result. So we've decided the events A and B. Now we need to decide which equation should we use. So we know Uy and we know Ay. We need to know one more thing. Do we know the final velocity? As a matter of fact, we do know the final velocity. When a body is at a maximum height, the final velocity is 0 in the y direction. It still has a velocity in the x direction, remember, but the velocity in the y direction becomes 0 at the maximum height. We saw this earlier. If the velocity at maximum height wasn't 0, it would be in the maximum height because it would either be going upwards or downwards. So we know that between A and B, Vy equals 0. Vy equals 0, Uy equals u sine theta, Ay equals minus g. So we can find the displacement using the third equation. So Sy, which will be the maximum height, is equal to, we'll use the third equation. So that will be Vy square, 0 square is equal to Uy square, u square sine square theta, plus 2as minus 2gh, because a will be minus g, which will give me the maximum height is u square sine square theta by 2g. So this is the final formula. These are the three standard formulas which you need to remember. But more importantly, it would be better if you knew how to derive them. Right? So in this way we can solve problems in motion in 2 dimensions by just resolving them into 2 perpendicular motions in 1 dimension. I'm just going to show you how to solve some more complicated problems. I'll not solve them, but I'll show you how this algorithm can be used. So you might get a question which is generally called a projectile on an inclined plane. So you can have an inclined plane like this, which has an angle alpha, and you can throw an object at a speed u at an angle theta, and I apologize for my drawing. It might go something like this, right? So in this case, you can either take the x and y directions to be the horizontal and vertical, but it's often more easier to take the x and y directions along and perpendicular to the incline. So you can take this direction as the x-axis, and you can take this direction as the y-axis. Again, what we'll try to find out is horizontal displacement, time of flight, and maximum height. So in this case, ux is still u cos theta, uy is still u sin theta. Ax and ay change. So let's see that. This is the acceleration due to gravity. And since this angle is alpha, this angle is 90 minus alpha, so this angle is also alpha. So we see that the acceleration in the x direction is minus g sin alpha, and ay is minus g cos alpha. Let's call these. It's always a good idea to name your events so you're sure between which two events are you applying. Now this is A, it has two components, this and this, whereas this and this are the x and y directions. So both the components are negative. The x component is minus g sin alpha and the y component is minus g cos alpha. So essentially I have solved the problem for you, because the things which we need to find out are basically the same and the conditions are the same. The time of flight will be the time between A and C, and in this case also between A and C the displacement in the y direction is 0. We see that AC is the displacement in the x direction now. X direction is not horizontal now, it's along the incline. So for time of flight the displacement between A and C should be 0. For the maximum height, the y direction velocity should be 0 at B, and for the displacement you need to find out the horizontal displacement between A and C. Right? So you can solve even more complicated problems, just the terms in the equations will become more complicated. The algorithm will remain the same. Right? Now there's one final thing which is generally useful, and that I'm going to try to show you, and that is we can also try to figure out for a given speed how we calculate the maximum range. So let's say I have a cannon which throws a cannonball at a certain speed, and I want to find out the maximum possible range. We know that if we throw it at a very small angle, it won't spend a lot of time in the air and it will reach the ground fast. As the angle is increased, it will spend more time in the air and it will reach the ground farther and farther. But as the angle is increased above a certain point, yes, it will spend a lot of time in the air, but it will not have enough horizontal velocity to cover a horizontal displacement. So we see that the angles 75 and 60 degrees, the range starts decreasing. So we need to find out the maximum range. That is the angle for which the range is maximum. So we can do that in two ways. We know the formula for the range. That is u square sine 2 theta by g. And we need to find out the maximum value given u and g. So the maximum value of sine theta is 1, which is when theta is 90 degrees. So the maximum value of sine 2 theta is 1 when 2 theta is 90 degrees, which is when theta is 45 degrees. Another way you could see was by differentiating with respect to theta. We know how to calculate the maximum and minimum of a function by differentiating it with respect to theta, right? Differentiate it and put it equal to 0. So we see that in this figure as well, that the maximum range is for 45 degrees. Right, so this is something which we were able to calculate using projectile motion. In the next lecture, we'll look at some relative motion and some concepts of frames of reference. Thank you.